Using AI to forecast and address conflicts within design and planning. On behalf of Michael Will, Brandon Arnold, and Priscilla Perez, I'm Scott Tribble. In this presentation, we aim to clearly lay out our main problem and present to you, the viewer, 3 unique solutions along with their respective risks and an analysis of their benefits. The use of AI as it relates to predicting and confronting conflicts in the design and planning stages is highly relevant to today's construction projects. Often in the design phase, conflicts are frequent as a result of poor communication, misaligned expectations of the stakeholders, and unplanned constraints. AI can help predict these conflicts by using historical data, running simulations, and so on. AI can be a tool used by all collaboratively that can enable everyone to explore a wide range of solutions while still early in the process. Conflicts during the design and planning phase are natural to the construction process and often difficult to forecast without errors. Using historical data, new plans, and stakeholder inputs to make designs, the process can be incredibly complex. The problems inherent to this issue are made even more prevalent due to undefined requirements, resource constraints, dynamic variables, and stakeholder misalignment. The repetition of the architectural tasks make it mistake-prone. With AI automation, it can eliminate those errors. In addition, AI can help predict conflict by using BIM software, showing where potential clashes may happen. Finally, the element of collaboration can keep all parties involved in real time, helping to eliminate problems that previously wouldn't have been discovered until later in the project. Solution 1. Regulatory conflicts. As previously discussed, poor communication, misaligned expectations of the stakeholders, and unplanned constraints can lead to conflicts during the design phase. For example, building code violations can be overlooked. This type of problem could stop a project. For example, if the design does not include enough space for a fire truck to pull up to a unit to deploy their ladder, the design is not in compliance. If there is not a ramp for someone in a wheelchair to enter one of the entrances, the plan is not ADA compliant. These are the type of problems our first AI solution aims to address. The AI solution we identified for this problem is a natural language processing model that has been trained to identify building code violations in design. Natural language processing can be used to interpret and cross-check your building plans against local building codes. We were able to find an existing software platform that can be used to do this. The software is called UpCodes, and UpCodes has the following features. Codes. This feature provides access to the building codes adopted for each jurisdiction, which includes all amendments and updates. Copilot. The UpCodes Copilot is an AI-powered research assistant. The AI can parse through building codes and provide insight. This enables asking assembly-specific questions to your jurisdiction, code year, and project-specific parameters. If you ask it questions, it will provide you with a summary. It can provide context and explain how codes will impact your project. The AI model is trained and updated with information as it becomes available. Projects. The project feature enables organizing the research around a project's specific requirements and facilitating collaboration among stakeholders. Diagrams. UpCodes is a building a library of detailed diagrams that illustrate complex code requirements. Search. The search feature enables looking up all required codes in one place. Code calculator. The code calculator enables confirming that a selection for a project is compliant and identifying necessary changes. Assemblies. UpCodes is building a library of assemblies. Their AI-powered search tool can be used to search for relevant assemblies. Products. The product feature enables searching for code-compliant products specific to your project. We identified one main advantage and 2 main challenges. Our risk analysis includes a recommendation based on those advantages and challenges. Under advantages, if the laws are not ambiguous and the natural language processing model has access to the most up-to-date building codes, it is a fast and accurate way to check the plans for building code violations. Under challenges, it is possible that the natural language processing model does not have access to the most up-to-date building codes. New codes and amendments are constantly being made. If the natural language processing model is not using the most up-to-date information, it could incorrectly analyze the plans. Upcodes says they keep the codes up to date as part of their service. This minimizes the risk. Under risk analysis, this seems like a good example of the type of situation that would benefit from collaboration between humans and artificial intelligence models. If there is no ambiguity and the codes are up to date, this is a very efficient way to check the plans for building code violations. If the codes are outdated and ambiguous, that is going to lead to errors. If a human can review the ambiguous codes and confirm the codes are up to date, that will increase accuracy. Floor plan generation and optimization. Digital drafting within the design planning phase can be quite time-consuming due to the integration of client criteria, building codes, and zoning requirements within drawing sets before construction. AI-powered applications can modify or create plans and simultaneously address issues related to design parameters and building code compliance to accelerate the floor plan workflow. Now, we will discuss a few applicable AI models. Machine learning learns patterns from large data sets in terms of design and planning that would include environmental factors, material factors, project data, etc., to suggest design choices, highlighting either past issues or accomplishments. For example, at a specific building site, historic patterns can reveal that usage of a particular lighting fixture within one floor brought intended energy saving costs. Therefore, it can be suggested to plan the same fixture within a different floor level of the same building. Generative AI trains on patterns from extensive data sets of existing design work. Then these models generate new design options and modifications such as floor plans. Generative models can propose solutions when parameter or compliance issues are detected by computer vision or NLP analysis. For example, alternative entrance or exits to meet ADA door clearance requirements, alternative wall locations to meet square footage requirements, or alternative window locations, each capturing a different view of the site. Graph technology, often combined with AI. In this application is relationship-based modeling relying on nodes, spatial objects, elements, walls, doors, rooms, etc., and its corresponding edges, complex relationships of dependency, adjacency, connectivity, etc., especially combined with AI, particularly GNNs, graph neural networks. It can reason and learn about spatial analysis to help automate detection and potential resolutions. Graph technology also helps with BIM, validation in terms of clash detection, design consistency, and design completion checking. Now, we will discuss a few AI web or cloud-based applications that provide floor plan generation or optimization. Architectures. A generative AI-powered building design platform to help design optimal residential developments in minutes rather than months, says architectures.com. Quantitative design criteria such as building regulations, dimensions, and typology are integrated into its generative process. This enables the AI integration of 2D and 3D models that can be changed or iterated as needed before AI produces a final BIM model. Finch 3D. This is an AI copilot capable of integrating with most design and drafting software available, such as Grasshopper, Revit, or Rhino. It utilizes AI in combination with advanced algorithms and graph technology for generative design and optimization. It supplies real-time feedback on performance metrics due to features for error prevention and automated code compliance. We concluded among the benefits are efficiency. It includes overall savings of cost and time of architect and designer labor due to AI assistance, including rapid design intent expressed between clients and architects and designers. Some web or cloud-based platforms have the ability for real-time collaboration to express clarifications or changes to scope. Some platforms also have templates or blocks provided for the designer to use. Integration of design criteria includes client requirements, parameters, codes, regulations. Such integration abilities can reduce errors and potentially prevent costly work in other project phases. With multiple design iterations, multiple schematic floor plans or other preliminary forms of drawings can be evaluated at a lower cost before committing to a more detailed construction drawing. Among its challenges are engineering constraints that do not seem solutioned with sample AI applications provided, suggesting difficulty in integrating MEP constraints. Possibly other platforms may have this ability or will be forthcoming. Building codes and regulations and how often and when do these get updated in real time or in the system is unclear. Generic overused solutions. General question of original creative design intentions and to what extent designers and architects will need to draft design themselves in the future, or how these certain roles may need to be replaced. Under risk analysis, we are considering these challenges: human knowledge and insight with regards to space, planning, material, finishes, building, code, zoning requirements, and general understanding of digital drafting is required to review of any drawings before client submission to prevent or mitigate any risk of AI errors or hallucinations. To recap, the primary problem we are reviewing is how AI technologies can be used to address and forecast conflicts within design and planning. Within the planning phase, scheduling conflicts arise for many reasons. Within the life cycle of a construction project, the schedule is created in the planning phase and consists of an estimate of how long the project will take and provides the expected sequencing of activities. Construction is fast-paced and new information arises daily. Scheduling conflicts are common and are usually a result from unanticipated delays in equipment, material delivery, weather, and manpower. These variables are hard to forecast and it throws off initial estimated schedules. This change of information requires a project manager to manually input new data and adjust the schedule week after week. Updating the schedule requires constant feedback from the field, manual entry into the scheduling software, and the distribution of this information to the project team. Predicting scheduling constraints requires either an experienced project manager or an AI-trained model. AI scheduling models, such as the implicit logic checker, can predict scheduling constraints and automatically generate revised scheduling updates. The AI technology this model uses is NLP, natural language processing, to analyze previously used construction schedules to automatically learn planning information that can be applied to existing projects. This eases the burden of time-consuming data entry and potentially eliminating human scheduling errors, such as the optimistic bias. AI software platforms such as Gantt chart AI help project managers ease scheduling conflicts. The Gantt chart is familiar to most construction professionals and is a commonly used schedule for construction projects. The Gantt chart is an AI-powered software platform that is also NLP-based. This model can be trained by supervised machine learning to generate construction project schedules. This model is based on historical data and operates within assigned parameters unique to each project. It automatically suggests schedules based on optimization constraints and can be used in pre-construction planning phases, but more importantly, it can be used throughout the construction phase. The dynamic modeling component helps small to medium-sized projects stay on track or get back on track. Another AI platform commonly used on projects is the N-Plan. This is a cloud-based AI platform that uses unsupervised and supervised machine learning to generate construction schedules based on historical data. This scheduling software is a probabilistic modeling type, which is useful for current projects by analyzing previous schedules for constraints and anomalies. Various disciplines, such as public utilities to new builds and various sizes of firms, could benefit from using this software. There are some risks to discuss when using new software. Privacy, the over-reliance on computers, and data accuracy are genuine concerns with using AI-powered software. The implicit logic tracker, Gantt chart AI, and NPlan offer risk management by automatically identifying constraints and anomalies. Privacy is another common concern for AI technologies. However, the previously mentioned platforms treat user data as proprietary information. Computer use will still require human oversight, but users should be careful to not overly rely on AI. AI technologies have demonstrated to be quite capable of aiding the human experience, especially on construction projects. Output data is only as reliable as input data. Scheduling platforms should require some human oversight, and when it comes to navigating, planning, and scheduling conflicts. In conclusion, AI streamlines building code compliance by providing tools for efficient code research, error reduction, and increased collaboration. The ability of AI to optimize or create floor plans while balancing design and engineering parameters will prove its reliability for achieving efficient, quality outputs. AI in scheduling platforms enhances project efficiency by optimizing timelines, resource allocation, and risk management for improved project delivery.